So I'm going to highlight some recent results that we've gotten in my group, where we're looking at the CESM large ensemble and the role of Arctic amplification compared to other processes in the warming climate. The model is the community Earth system model, courtesy of NCAR in the university community. And all of the work presented here was done in collaboration with Yannick Peng here at UC Irvine, and our work is supported by NSF. You could change the slide, please. Thank you. So this is the same plot as Eva just showed, and this is from his 2014 paper. And it gives the different processes acting in the winter northern hemispheric circulation. Indeed, the mid-latitude circulation is complicated. Next slide, please. Emily, thank you. And and internal variability is very important, as we were reminded of in a comment by Wallace et al. In Science magazine in 2014. So it is therefore very attractive, next slide please, to use a large ensemble of simulations. By averaging over the ensemble members, we can average out the stochastic noise and examine the force signal. So this is the CESM large ensemble, as I said before, consisting of 14 members of fully coupled simulations run over the time period 1920 to 2100, using historical forcings to 2005, and then following the RCP 8.5 scenario. So this gives us an opportunity to examine in a robust way how the mid-latitude climate responds to a strong Arctic sea ice decline. Specifically, we can examine whether the Francis and Vavres mechanism holds up when we can isolate the force signal. So this is a cartoon from their paper 2012, and it shows how they project the contours, geopotential contours, to be enlargening, getting more wavy in a future climate. Next slide, please. So this shows some results. There is indeed a strong signal in terms of sea ice loss that's shown on top there. This shows the evolution 1920 to 2100 on the x-axis of the annual mean of the 40-member ensemble mean sea ice anomalies. They are relative to 81 to 2010. And the blue represents the ensemble spread. So this is a robust signal. And down here, I show the time evolution, again, 1920 to 2100, of surface temperature anomalies relative to early in the century, 81 to 2010, as a function of latitude. So this is to highlight the Arctic amplification signal. You can see how the poles are warming as we go on. And actually, the signal saturates there at about 2050 or so. Next slide, please. I will show the results, always in terms of the ensemble mean of change between the two 30-year periods at the end of the century and the beginning of the century. And I'm going to focus on winter, and that's what is shown here. This shows the January, February, March mean sea ice concentration signal at the end of the century. So you can see the extensive loss of sea ice. And on the right, there's firstly the response in terms of surface temperature, and then in geopotential, 500 hectopascal geopotential height. And as you can see, in terms of temperature, there's massive warming in the Arctic. And but the dynamical response is not in terms of the northern annular mode as we're used to seeing. It's more complicated, and it's reminiscent of a wave train. On the right-hand side, we show the response in the lower stratosphere. These are the zonal winds at 10 hectopascal, and the climatology is shown in red contours. So you can see that there is a decrease in zonal winds where the stratospheric polar vortex is, so it's slowing down the polar vortex. Next slide, please. I'm going to show the change in the mean zonal flow here in terms of the zonal index. It's simply defined in terms of the mean geopotential height averaged over two latitudinal belts. So we take the average over 20 to 50 north and subtract the average over 60 to 90 north. So that's our zonal index. And the positive zonal index corresponds to a reinforced westerly flow and vice versa. So it's highly correlated with the NAM and NAO indices. So a positive index corresponds to a positive NAM and a negative index to a negative, or a decreased index to a negative NAM. And here is the, on the left-hand side below here, shows the response in terms of this zonal index through the annual cycle. Now I'm concentrating on the winter response here, so let's look at the winter time, January, February, March on the left. And as you can see, there's really no, there's no significant response. It's close to zero. And you can see the spread of the ensemble members. It shows the large spread here, and it's really not significant. However, if you look at sectors, this is for the zonal mean on the left-hand side. What's shown on the right-hand side is the evolution of the zonal index in different sectors. So in black is the northern hemisphere, which we show on the left, and then we show the Atlantic sector, 90-degree longitude sectors. Atlantic, Asia, Pacific, and North American continent. So as you can see, the American continent stands out in that you have a negative zonal index there in the wintertime, whereas the others are close to zero and even slightly positive in the Atlantic. Next slide, please. Let's look at the waviness in the flow, or sinuosity, because the waviness is really what people concentrate on when they think about the Francis Vavre's mechanism. And sinuosity here is defined in terms of the length of the average 500 hectopascal geopotential isoline within 30 and 70 degrees latitude. So it always corresponds to the average at about 50 degrees latitude, regardless of season and so on. And down here on the left, we show again the annual cycle of this sinuosity. And as you can see, this is consistent with little change or slightly positive change in the zonal index. There is very little change in the sinuosity here in the zonal average. However, in wintertime, however, if you look at the sectors, again, the American continent stands out in that there is an increase in sinuosity, meaning there is wavier flow over North America compared to the rest of the Northern Hemisphere, and there's slightly negative, although it's hard to talk about significance here. These are small trends in the other sectors. Next slide, please. So this, for the Northern Hemisphere average and for the sectors, except for the American continent, it does not support the Francis Vavre's hypothesis. But it is interesting how variable it is depending on where you're looking. Next slide, please. So this shows the zonal mean westerlies in a latitude height cross section. So this is the average difference between end of the century and beginning of the century in color shading, and the climatological flow is shown in gray contours. So as you can see, what is happening at the end of the century, there is like a squeezing of the eddy-driven jet. So it's being squeezed from both sides and getting stronger actually in the core. It's a very interesting signal because that would correspond to less waviness. If you have a stronger jet, stronger jet, that would indicate less waviness actually. So again, this is comparing the last 30 years of the century to the first 30 years. So the question is, when does this effect kick in? Next slide, please. So this is a Hosmer type diagram. Along the x-axis, we have time, so from 1990 to 2100, and latitude on the y-axis from low latitude to the poles. And what is shown here is anomalies in winter mean, zonal mean, 700 hectopascal zonal wind. So as you can see, the zonal mean, the squeezing of the jet from both sides occurs around 2070 in the large ensemble. So this is averaging over all of the ensemble members. Next slide, please. So what's happening sector by sector? Because we saw this interesting signal in one of the sectors. The northern hemispheric response is shown on top there on the left-hand side. Again, this is the same figure as before. And you can see that it's really the two ocean basins that are contributing to the signal. The Atlantic and the Pacific shown in the lower left. Okay, so this is where the squeezing of the jet is occurring. Actually, over North America, we have a negative NAM type response. So the narrowing and reinforcement of the Atlantic and Pacific jets, or this that we saw in the zonal mean, is really taking place over the Atlantic and over the Pacific, where the storm tracks are the most active. Next slide, please. Let's look at the change in thermal mean, or change in the zonal mean thermal structure in latitude height cross sections. On the left-hand side, I'm talking about the upper left figure now. This is temperature in the pressure latitude cross section. If you look at the North Pole, you can see AA, Arctic amplification there. And what is also depicted is the UTW, or the upper tropospheric tropical warming, that is very substantial, and it's a very robust global warming signal. So we get this Tucker warp in the northern hemisphere between Arctic warming and the upper tropospheric tropical warming, both eating at the jet from different sides, so to speak. Okay, and this contributes to an asymmetry between the two hemispheres, and that's shown below here. This is the annual cycle, so we go from, let's see, this is summertime. We put winter in the center. So it's June, July, August. And if we look at the southern hemisphere first, you can see the shift of the poleward shift of the jet. Okay, the red indicates that it's strengthening, it's shifting poleward. That's not occurring in the northern hemisphere in winter. As you can see, there is the narrowing and of the jet and strengthening of the jet in the winter. So the main asymmetry between the two hemispheres is that we have a large continent in the southern hemisphere, and we don't have an Antarctic amplification like we have in the northern hemisphere. So next slide, please. So this is actually something we've looked in the CMIP-5 model. So when we average over, I can't remember how many, there were more than 30 different CMIP-5 models that we averaged over. And each has a different climate sensitivity, so this is not a model-dependent result. We see the same kind of sharp reinforcement and narrowing of the jet, both over the Atlantic and over the Pacific. Next slide, please. So my take-home message, I don't want to be too long here, is that the CESM large ensemble, as well as the CMIP-5 global climate model, show a decrease in waviness in mid-latitudes in winter at the end of the century, rather than a simple poleward shift of the jet, such as was seen in the CMIP-3 model projections. So it's the competing influence of Arctic amplification as well as the upper tropospheric tropical warming on each side of the jet that results in this narrowing of the jet. There are other effects that I haven't mentioned here because of time limitations, but there is also a stratospheric response that we think is very important in shaping the circulation. And in fact, we are running all of our perturbation experiments with a high-top model, or WACOM now. And we're also examining new ways of forcing the model, including with heat flux forcing rather than sea ice or SST or snow forcing, and using nudging to get at the Arctic amplification directly rather than indirectly. So thank you.